TPU is a wonder 3D printing material. It's flexible, tough, and incredibly resilient when used in demanding applications, and it's found a home in combat robots at a small scale because, believe it or not, it's actually an incredible armor and holds up to a lot of abuse. But a lot of people are scared to 3D print TPU because of horror stories about it jamming up extruders and destroying hot ends. And I'll be honest, printing TPU used to be a real challenge, but we've come a very long way. So in this video, I'm updating a 5-year-old video I did about printing TPU, show you how you can print it successfully on almost any 3D printer. And as a bonus, I'll share with you my advanced printing settings for creating extremely lightweight but durable 3D printed TPU frames for my combat robots. Let's get started. How's it going, guys? Angus here from Maker's Muse, and welcome back to another 3D Printing 101. So what is TPU and what makes it so different to other materials you can 3D print with? Well, TPU stands for thermoplastic polyurethane, and it's flexible. This is a flexible 3D printing filament, which means whatever you print will have that flex and give to it, which lends TPU prints incredible resilience. You can stretch these, pull these, run over them with a car, and they just spring back into place, which is a fantastic property when you need something that can hold up to abuse, like with combat robots. But this flexible nature means that, of course, the material that's on the spool as you're printing with it is also flexible. And depending on what sort of 3D printer you have, this could be problematic because as the material is being forced into that hot end through the extruder, well, it wants to flex. It's like pushing a wet noodle through a tube. And this flexible nature means that on some 3D printers, printing in TPU can be really challenging or almost impossible. And let me explain why. Imagine you have your extruder here and the hot end, and there's a gap between the gears of the extruder and that hot end. The filament up to the path of the extruder is being pulled off the roll, so that's not so much of a problem. You can pull the flexible material, and like a rope, it'll just tug along and feed into the extruder, no problem. It's when it's being pushed out of those extruder gears into the hot end that you start to encounter an issue. Because this material is flexible, it'll bend and shift and try to find the path of least resistance. Instead of being pushed through the hot end and melted, it'll try to spill out the side, or tangle around the gears, or just strip in the gears entirely because it's so soft, and your print fails. So this is the reason that old extruders and 3D printers used to struggle so much with TPU, but it's not the only reason we used to struggle so much. This is because TPU isn't what it used to be. 3D printing materials have evolved a lot since the early days. Back in the day, PLA was just PLA. It had this awful, clear, sort of straw-colored look to it. It was very brittle, and TPU was just TPU. It wasn't modified in any way to make it more suitable for 3D printing. It was very soft, very flexible, very elastic, which means trying to print with it was very challenging unless you had dedicated hardware. But now we have TPUs that have been modified specifically to make them more suitable for 3D printing. As an example, this is Polymaker's High Flow TPU, and it has a shore hardness of 95A. The shore hardness of a material is how soft or hard it is essentially, and depending on where it falls on the scale, you can have very, very soft, flexible filaments, all the way up to filaments that are very, very rigid almost, and only have a little bit of give to them, and depending on where they fall on the shore hardness, will determine how soft or hard they are, and there's different grades, but shore hardness A is generally how you'll find 3D printed TPU measured. 95A is actually still pretty flexible. If you go any lower than that to something like 90 or 85, you're getting into the murky waters of very flexible, difficult to 3D print materials, because these TPUs will be very elastic, which means they'll easily stretch around extruder gears and deform before going into that hot end. But these heavily modified TPUs, like the one from Polymaker, have much less elasticity than the older soft TPUs that we used to have to work with, which means they don't deform as much. But they still can, which takes us to extruder geometry and another big step into making TPUs easier to print. As I said, you have the extruder gear and the hot end, and that gap is where the TPU can deform and find the path of least resistance and escape. Modern extruders, if they're designed well, will have a sharp angle on the tube leading into the extruder and out of the extruder into the hot end. This means that there's no way for the filament to deviate from that extruder gear. It goes straight in, and then it's forced straight into the hot end, with no way to deviate out of that tube. The only way that that TPU can fail is if it squishes too much in that extruder, and then will either gum up and jam, or if your extruder isn't gripping the filament tightly enough, it can slip and then the print can fail that way, but it's not going to deviate and spill out the side of the extruder assembly like we used to see in the past. The two innovations in material science and the extruder geometry means that 3D printing with TPU is way easier than it used to be, and there's a few things that you might still be doing if you've been printing for a while that you probably don't need to do anymore. The first thing is disabling retractions. The general practice back in the day was to disable retractions when printing with flexible filaments, because you imagine you're fitting this filament in and then pulling it out, pushing it back in, pulling it out, pushing it back in. You're dealing with a flexible material, so that just greatly increased the chance of the print failing because you're ruining that nice continuous path of filament being melted into the hot end by retracting it. But with a fully supported extruder and these harder TPU blends that are on the market now, you can print with retraction, which greatly reduces stringing. Doesn't fully remove it, but it does greatly reduce it. Stringing is still an issue with flexible filaments. This is just because of the nature of the material. When they're molten, it's very hard for the filament to stop flowing in the hot end, and you will get wispy stringing. So to remove as much stringing as possible, what you should enable in your slicer is to avoid crossing perimeters, or in Cura, it's known as combing. This means that during travel moves, the actual hot end will move within the boundary of the print as much as possible. So therefore, if there's any stringing, it'll be within the print itself versus moving between 2 points, which might be more efficient in a straight line, but you'll get stringing between those points. The second way to remove as much stringing as possible from TPU is to dry it. Yes, TPU absorbs moisture from the air, just like so many other 3D printing filaments, and you should dry it for optimal results. It won't remove all stringing, but it helps a lot to remove the worst of the stringing and bubbling, because when TPU is so waterlogged, it will actually boil the water off as it's printing, which creates a foamy, messy looking print with heaps of stringing, and that will definitely destroy the structural integrity of the print, as well as looking pretty awful. So try to store your TPU in a sealed area with desiccant to keep it dry, or consider drying it with a dry box. Or personally, I still use a cheap food dehydrator and run it for a couple of hours to dry my filament, and it does make a very noticeable difference indeed. The next thing I really want to talk about with TPU printing is support material, because believe it or not, with these newer blends of TPU, improvements in slices and improvements in machine geometry and design, you can print support material that pulls away in TPU. It's incredible. It used to be the way that you'd avoid printing with support material at all costs when printing with TPU, because it would weld to the print and you'd have to mechanically cut it away. But thanks to these improvements in the material science and the slices themselves, I found that yes, support material does pull away, and I'll give you a live demo right now. This is a new frame for my Antweight robot pancake, and this support material here, where the blade sits, I can't print this in any other way that doesn't need support material. It needs this supported area right here. So the trick with removing TPU supports is you grab an edge with as much purchase as possible, and essentially like Velcro, pull it away to separate the two layers. It's incredible what you can do with support material in TPU nowadays if you have a suitable 3D printer. This was printed on the Prusa Mark IV, which I found is very good at printing flexible filaments. But I actually recently successfully 3D printed TPU on the Ender 3 version 3 SE, which is a budget price 3D printer with a direct drive extruder. And that printed this kind of TPU with no problem at all. The trick I've found with TPU supports is you want to try to support large areas that are flat. Make sure you untick don't support bridges in your slicer, because that'll only support the edge of the 3D print. And what I find is that the bridges do droop quite a lot because it's flexible filament, it's quite soft when it's molten. I find that actually results in a much worse surface finish than supporting the entire area with support material. And as you saw, it pulls away like Velcro, except in some of the corners where it might melt together and you might need side cutters to remove it. But when it comes to creating incredibly light, durable TPU prints, what settings should you use? Well, I've created my own custom profile for TPU that I use in my Antweight combat robots to make them as lightweight but as strong as possible. So what I'm going to do now is just walk you through my settings in PrusaSlicer and explain my reasoning. So what we have here is the frame for my Antweight robot pancake, and this is what it looks after slicing it with the G-code preview. Now, if you've sliced models before in PrusaSlicer, off the bat, you might notice some odd looking things as we scroll through the layers of this 3D print. And I've changed quite a few things that I've found over time of making these machines and competing with them that actually makes a big difference to durability and lightweightness, if that's a word, of these frames. You can see that with the support material disabled, that this frame will weigh 39 grams using my settings. And if we change to the 0.2 structural setting out of the Prusa Mark IV, which is a default, then you see it uses 43, almost 44 grams of filament. So with my modified settings, you end up with a lighter weight frame that's just as durable, if not more durable, for what you need in combat robots. Let's run through the settings. We've got a layer height of 0.2. This is a combat robot part with a fairly geometrical design, so I find that a 0.2 layer height is fine. And then with perimeters, 1 perimeter. This is the weirdness that I'm starting to introduce into my model, and it'll all make sense when we go into the advanced settings. So 1 perimeter, keep that in mind. Horizontal settings, we've got a top of 4 layers at 0.2 and a bottom of 4 layers at 0.2. So with the combat robots, I like to do really thin top and bottom walls. This is the minimum I would go to because we're starting to get hammer saws in our competition and they punch right through plastic and TPU with no problem. So if you're trying to get a stronger part, I wouldn't increase these as such. I'll try to increase air armor, which is where we come into infill. So for the infill of this model, I have a cubic infill versus the standard rectilinear infill that you'll find with the default profile. The reason cubic is important is because it's a 3-dimensional infill. So imagine you're printing a cube out of TPU and you use a rectilinear infill. Well, this is essentially 2.5D. It copies the same pattern up all the way through the part, which means that when you squish that cube, it's not going to squish uniformly. It'll actually resist quite a lot from the top down, but actually will squish really easy from the side because it's essentially going to squish into a parallelogram because there's not much resistance there. But with cubic infill, it's a 3-dimensional infill, which gives you a uniform amount of squish, I suppose, around the entire part. 10% is very, very low, but PrusaSlicer does some really clever stuff where it adds internal bridging to support geometry that forms over areas that don't have infill. So don't worry about having to have infill so high that supports areas that form in the print, because PrusaSlicer does some clever stuff to bridge and support those areas anyway. Now, as I mentioned, this part does need support material, but what I've actually done is I've used manual support painting, paint on supports, to make sure it's only where I want. Now, I haven't actually painted on where I want it, I've painted on where I don't want it. Because as I mentioned, you can support prints with TPU now. It will pull away, but it's not super easy, so you want to avoid it where possible. The back of my model here has some geometry where, look, it's a bore, it's a little hole there. It doesn't need support material, it'll print just fine. So I've just gone around and right-clicked to basically use the red don't put support here, to support blockers, make sure there's no support there, and I've left support material generation on auto, but I've made sure to enable support on build plate only, because I don't want any support in the model itself. I've designed the geometry specifically to not need it. Now, in terms of what support type, I actually went with snug. I did a video recently on support snug settings, and this is essentially default. I haven't changed the snug pattern. The top Z contact Z distance is 0.2. Now, you saw how it pulls away like Velcro, but sort of gets stuck in the corners. If you're finding your parts don't release, you could potentially increase this, but you'll end up with a pretty poor surface finish on the underside of those parts as they're resting on support. So 0.2 works for me. I haven't had to change that. I wouldn't go any finer because, again, TPU loves to stick to itself, but the top contact Z distance of 0.2 works for me. And these support settings, for me at least, work really well with these modified TPUs like the Polymaker High Flow TPU. Next up, we have speed. I've left this default. This is the Mark IV running the Linear Advance, and these are very fast printing speeds. But again, high flow. These are modified TPUs, and they can handle the speeds no problem. I haven't had any issues with under extrusion or prints jamming up and failing when printing with these high flow TPUs. The much softer ones, yes, you might have to slow down significantly for any chance of success, but 95A or any higher, no problem at all. You can print at full speeds, unless you have a Bowden extruder. Now, I've tested this material on Bowden extruders and it does work, but you will probably have to slow down because with a Bowden extruder, your extruder's here, and you have a long tube all the way to the hot end here. That's a long way to push a flexible filament. Again, spaghetti, like flexible spaghetti down a tube. It wants to buckle and kink and jam. You'll have to slow things down. But with a direct drive extruder that's any recent sort of design, I haven't had any issues printing very, very fast, essentially normal speeds with these modified TPUs. But now we get to the weird stuff. This is my changes to the extrusion widths. You would be forgiven for thinking that a 3D printer with a 0.4mm nozzle extrudes 0.4mm lines, but that's actually not the case because the 3D printer can push more material through that 0.4mm nozzle to create wider extrusion lines. It can't push less, like you can't end up with a 0.3mm line out of a 0.4mm nozzle. That's not going to work, but you can push 0.42, 0.5, or in my case, with my single external perimeter, 0.8. So this essentially is doing a single line, but at the same thickness essentially as two perimeters. Sounds bonkers, but what I've found with TPU is that thick single line makes these parts very, very resilient. And there's another major reason I shifted to doing a single external perimeter versus more multiple internal perimeters. Because you see I've left the internal perimeters at 0.45. And that's because if we go to our G-code preview, you'll see one of my bugbears with PrusaSlicer, and something that you cannot change currently, or possibly ever, but something I've kind of worked around. Let's scroll through the layers down, 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 and have a look down here. So here, where it's orange, you can see my thick 0.8mm external perimeter. But then, what's this purple doing? You see this purple line here as the part builds up. We've got our bottom surface, but then what's all this going on? Well, you see, when there's an overhang, PrusaSlicer will add additional perimeters in to support that area to make it print optimally with the best finish and success rate possible. You can't disable this. You cannot disable this. There is nothing you can do to disable it. There's no setting. There's these settings where it says extra perimeters if needed. That doesn't matter. I don't have that ticked. It doesn't change it. You still get this in even the latest version, 2.7. I would love an advanced setting to disable this, because in cases like this where the robot's weight is very important, this is adding weight. And I don't really care about the surface finish. I can do things to change that. But by having a single thick external perimeter, I've got this nice thick external line here where it goes straight onto my 3D infill. And you can see that infill forming. That very sparse but three-dimensional cubic infill is a really nice way to make a part that's flexible in essentially all directions. But like I said, it's very sparse. So areas where these bores form that need to be supported, PrusaSlicer just chucks bridges in between those sparse infills, and then the part forms on top of that, like that. You can see it's very, very clever. It doesn't need a dense infill to support details like that. Not anymore. Back in the day, crappy slicers needed it. That's not a thing anymore. And you can see that this support material as it forms is very, very coherent. Now, I'll disable that setting that turns support material off when there's bridges, because if you don't do that, you'll have a big hole here. And then as that top surface of the part is formed like that, you'll end up with nasty sagging. And actually the support material is harder to remove than actually just having a full slab of support material. So that's how I do it there. And then it goes all the way up like that to the top. And that's how I slice my TPU prints to make them as durable as possible while being as lightweight as possible. There's so many more tips and tricks I could talk about in terms of making these little ant weight robots as durable as possible. So if that's interesting to you, leave a comment in the description below. But for now, please do enjoy a compilation of this machine and many others in our latest little ant weight competition here in Australia. And I'll catch you guys in the next one. Bye.